So just like when we talked about radicals, complex numbers also have conjugates, and they have the same exact idea. If an equation is written in the form a plus bi, its conjugate is a minus bi. And the converse is also true. If an equation is written as a minus bi, its conjugate is a plus bi. So if you see a question that says write in standard form, just like we can't have radicals in the denominator, we can't have imaginary numbers in the denominator either. So let's rewrite 3 plus 4i over 5 minus I. To multiply by the conjugate, we just change the subtraction in the denominator to addition. So this should be 5 plus I. We're going to have two different things that we're going to have to multiply out. We'll start with the denominator. I always write the sign in front of the second term when I use the box method so I don't accidentally drop a negative sign. 5 times 5, we get 25. Negative I times 5 is negative. The rational number goes first, so 5, and then I, negative 5i. And then 5 times I, we get 5i. And then negative I times I, remember we said I squared equals negative 1. So this is like negative 1 times negative 1, or negative negative 1. That becomes positive. And when you use a conjugate, the imaginary numbers should drop out. So we have negative 5i plus 5i, that equals 0. Perfect. That's what we want to happen. So then to simplify the rest of the denominator, we just do 25 plus 1, which is 26. Make a little bit of space here so we can use the box method again to simplify the numerator this time. So we're still going to have to multiply 5i, or 5 plus I, but this time we're going to multiply by 3 plus 4i. Five times 3 is 15. 4i times 5 is 20i. 3 times I is just 3i. And then 4i times I is 4i squared. And then we said that I squared equals negative 1. So this is the same as 4 times negative 1, which becomes 4. Oh, sorry, negative 4. Add the rational numbers together. So 15 plus negative 4, or minus 4, equals 11. 20i plus 3i, just add the coefficients. That equals 23i. And the last step, let's not forget to answer the question. 23i is the numerator, 26 is the denominator. 11 plus 23i, I'm sorry. So the final answer is 11 plus 23i over 26. Same thing for this second example, only this time it's 3 minus 2i. So we would simplify this by multiplying by the conjugate of 3 plus 2i. So again, we're going to do the box method 2 times. One for the numerator and one for the denominator. We should get 9, negative 6i, positive 6i, and then negative 2 times 2 is negative 4. I times I is I squared. I squared equals negative 1. So negative 4 times negative 1, we should be getting positive 4. Add the rational numbers together. 9 plus 4 is 13. And then negative 6i plus 6i, those should cancel. Negative 6 plus 6 is 0. That's what we want. So 13 is our denominator. Next, multiply the numerator. So 5 plus 2i times 3 plus 2i. 5 times 3 is 15. 3 times 2i, 6i. 5 times 2i is 10i. And then 2i times 2i is going to be 4i squared. But we said that I squared equals negative 1. So this is the same as 4 times negative 1, which becomes negative 4. Add the rational numbers. 15 minus 4, we get 11. Add the complex numbers or imaginary numbers. 6i plus 10i, we get 16i. So then the numerator is just 11 plus 16i. All right. Next, we want to talk about graphing. So before we've learned ordered pairs as x, y ordered pairs. It's going to be the same concept. This time we just have two different planes as our real plane and our imaginary plane. So the first number is 3 for this first example. That means we go to the right 3 spaces. And you can think about the imaginary as kind of like the y-axis. So we go to the right 3 and then we go down 2. And plot our point. And then for the next ordered pair, it's negative 2 plus 4i. So this is like x, go to the left 2. The 4i is like y, go up 4. Left 2, up 4, plot our point. And then negative 5i, you can think about that as like 0 minus 5i. So you don't go left or right at all, you just go down 5. And plot. The last topic we're going to look at, the absolute value of a complex number. Z equals a plus bi. You'll see that written as the absolute value of z is a non-negative real number defined as a squared plus b squared square root of that sum. It's the distance between z and the origin on the complex plane. Let's look at a couple of examples. We are being asked to find the absolute value or distance from the origin of 5 minus 2i. Step 1, or 12i, I'm sorry. Step 1, Find your constants. A equals 5. B equals negative 12. I'm going to come back to the previous slide. We said that the absolute value of z is the same as a squared plus b squared. We have a and b picked out. Now we just need to substitute it in. So the absolute value of z equals the square root of 5 squared plus negative 12 squared, which is the same as square root of 25 plus 144. 25 plus 144 is 169. So then the absolute value of z equals 13. Second question, same thing. Figure out what A is, figure out what B is. So I see 17i, but just like when we plotted the point negative 5i, that just means our A is equal to 0. You could think about this as like 0 plus 17i. So here's A, here's B, A equals 0, B equals 17. Substitute it into the formula. I think the 17 squared is 289. You can correct me if I'm wrong. But ultimately, I know that the square root of any number squared just becomes itself again. And there you have it. Good luck. Let us know if you have any questions.